In this video, we're going to take a look at exam revision for integration. So what we're doing here is just covering everything that we've done so far, such as basic integration, definite integrals, finding functions, and then finding the area under a curve using integration. So let's just jump straight into the first question here. So we're given this integral of kx squared minus 2x from 0 to 3 with respect to x is equal to 27. We just want to find the value of k. Now it should really say here that k is just a constant. So if k is a constant, then we can just integrate like normal, going term by term here. So this is a definite integral, so we're going to have square brackets. So if we go term by term, remember we just add 1 to the power and divide by the new power. So we're going to get kx cubed here over 3. So add 1 to the power to give me a power of 3, and we divide by that new power. Minus 2x here, so when we add 1 to the power, that would give me minus 2x squared. Then we divide by that new power. Once we simplify, we're going to get minus x squared there. And we know the limits here, that's from 0 to 3, so 0 to 3. Now we're told the result of this, okay, that we can see here is equal to 27. So that's equal to 27. So what I'm going to do now is substitute these limits in, okay, simplify, and then we should be able to solve for k. So if I substitute 3 in here, what I'm going to get then is k lots of 3 cubed. So 3 cubed would be 27. If we divide that by 3, then we get 9. So what I'm going to get here is 9k. So we get 9k minus x squared. So x squared in this case would be minus 3 squared. So minus 3 squared would be minus 9. Now when I substitute in the lower limit here, if we think about this, well that would be k times 0 cubed, so that would be 0. Doesn't matter what we divide it by, that result will be 0. And then minus 0 squared. So I don't need to worry about the lower limit here. Once I substitute that in, it just evaluates to become 0. Okay, so we'll need to consider the upper limit here. So I get 9k minus 9 is equal to 27. And at this point here, now this is a nice straightforward GCSE equation. So all I'm going to do now is add 9 to both sides. So I get 9k is equal to 36. And then divide both sides by the coefficient of k, which is this 9. So we get k is equal to 36 over 9, which would give us 4 there. Okay, so the value of k for the first question is 4. Moving on to question 2 now, where we're looking to find a function using integration. So what we've got here is the gradient of a curve, which we can see is given by f prime of x. And we're also given that the curve passes through this point 2, 10. So using that information, we want to find the equation of the curve in this form, y equals f of x. The first thing I'm going to do here now is take my f prime of x, we're going to integrate that, and that would give me f of x. But we need to be careful because we won't have any limits on the integral, so we're going to get a constant of integration. And we need to use this point here to find the value of that constant of integration. So let's start by integrating f prime of x here. So we're integrating 12x squared, so 12x squared, minus 6x here with respect to x, but we don't have any limits on the integral, so that's why we get our constant of integration. So this should hopefully be a nice standard integral here, just go term by term. I'm going to get 12x cubed over 3. We'll simplify in a moment, and I've got minus 6x here, so if we add 1 to the power and divide by that new power, we get minus 6x squared over 2. Okay, and because we have no limits on the integral, we need our constant of integration. So if we simplify here, I'm going to get 4x cubed, so 4x cubed. I've got minus 6x squared over 2, so that would be minus 3x squared. And then finally we've got our plus c here, our constant of integration. So this is f of x. So what I need to do now is evaluate what c is here, our constant of integration. And we can do that using this point here, okay? So when x is 2, we get that f of x is equal to 10, okay? So in that case, let's substitute everything in here. So I get 4 lots of 2 cubed minus 3 lots of 2 squared plus c, and that's all equal to 10, okay? So let's evaluate here. So 2 cubed is 8, times that by 4. 8 times 4, I get 32. I've then got 2 squared, which is 4, minus 3, so I get minus 12, and plus c, and this all equal to 10, okay? 32 minus 12, that would give me 20, so c plus 20 is equal to 10. And in that case then, we get that c is going to be equal to 10 minus 20, giving me minus 10. So in that case then, what we get here for f of x, so f of x is equal to 4x cubed minus 3x squared, and then plus c, where in this case c is minus 10, so minus 10 there. Okay, so that's our f of x, but we need to give the answer in the form y equals f of x. So therefore, all we need to say then for our solution is y is equal to 4x cubed. So 4x cubed minus 3x squared minus 10 there. Okay, and there we have it. So that's our solution to question 2. Moving on to question 3 now, what I've got here is a diagram of a sketch of the curve C. So this is the equation of C here, so y equals x times x minus 1 times x minus 3. So we've got this cubic polynomial. And we've got the finite region here that's shown shaded, and that's bounded by the curve C and the x-axis. So we can see that here, okay? And then underneath the x-axis here, we want to use integration to find the total area of the shaded region. Now we have to be very careful when we integrate here, because what we need to do essentially is break this up into 2 parts. So I've got the part from here to here that's above the x-axis, and then I've got the part from here to here that's below the x-axis, okay? So I'm going to consider these now in 2 parts. I'm going to call this part here above the x-axis as R1, the region R1, and then this part from here to here that's below the x-axis as R2, okay? Now the reason we're splitting this up here is because obviously once I integrate here, or from here to here, this area, or this shaded region will be negative because it's below the x-axis, okay? So obviously we need to negate that and take that as positive. So what I'm going to do then is consider this in 2 parts. So R1 here is going to be the integral of our cubic polynomial, so x times x minus 1 times x minus 3 with respect to x. But we need the limit. So what would these limits be here? Well, this one here will clearly be the origin. So the lower limit will be 0. But the upper limit then, we need to deduce what that is ourselves. Now this is already in fully factorized form, so it's quite straightforward. I'm going to get 3 solutions here. So I get x equals 0. That's this point here. And then get x equals 1, which must be this point here. And then finally x equals 3. And that'll be that point there. So all I need to actually do now is just expand this cubic polynomial. So my upper limit here for this R1, or this region R1, will be this 1 here. So if we expand this here, let's just do underneath. So x times x minus 1 times x minus 3. Well, expand these 2 terms first. So x times x gives me x squared. So x lots of x squared. I get minus 3x and then minus another x. That's minus 4x. And then minus 1 times minus 3 gives me positive 3. So if we now multiply 3 by the x, I get x cubed. X cubed minus 4x squared. And then finally plus 3x. Okay. What we're doing now is we're integrating this here from 0 to 1. Okay, so just replace the fully factorized form with the expanded form now. So R1 is going to be equal to the integral from 0 to 1. Remember the limits here are 0 to 1 because we're integrating from this point here 0 to this point here, which is 1. So it's going to be x cubed minus 4x squared plus 3x. And this is all with respect to x. So again, just go term by term here. So I'm going to get x to the 4 over 4. X to the 4 over 4. I've then got minus 4x squared, so that'd be minus 4x cubed over 3. And then plus 3x squared over 2. 3x squared over 2. We have our limits here from 0 to 1. So I need to substitute these limits in here now from 0 to 1. Remember, we start with the upper limit. But the good thing about this question is once I substitute in the lower limit here, that will all be equal to 0. So in that case, we only need to consider the upper limit here. So in that case, we're going to get 1 to the power of 4 over 4. So that'd be 1 over 4. We then get minus 4 lots of 1 cubed. So that'd be minus 4. And that's all over 3. And then finally, we've got 3 lots of 1 squared. So that'd be 3 over 2. So plus 3 over 2. What I need to do now is put this into my calculator here, just to evaluate this. So if we do this here, I get 1 over 4 minus 4 over 3, and then plus 3 over 2. And if you do this correctly here, what you should get is 5 over 12. So 5 over 12 here, this is for R1. Okay, so this region here is 5 over 12. So put that up here, R1 is 5 over 12. just so you can take a note of that. What I need now is R2. So R2 is between 1 and 3. So what I'm going to do now is integrate this curve again. Okay, so we've got the expanded form here. So x cubed minus 4x squared plus 3x with respect to x. So this time it will be from 1 to 3. Now if we think about this, I've already done this lower limit here. Okay, when we substitute in 1, we got 5 over 12. So what I need to do here now is just substitute the upper limit in here, this 3, for the integral, which we already know. So we're going to get this now. So it's going to be x to the 4 over 4 minus 4x cubed over 3. And then plus 3x squared over 2. Okay, and that would be from 1 to 3. Like I said, we already know what the 1 is when we substitute that in. So all I need to do is substitute 3 in, simplify that, and then subtract 5 over 12. Okay. Now we're going to run out of room for this. So what I'm going to do is I'm just going to clear the screen here. Will we have enough room? Let's try and do it here. Okay, what I'm going to do is I'm just going to rub out the bit above just so we do have enough room. So I'll just get rid of this here just so we can see we've got R1 above. Okay, let's see if we've got enough room here. So substituting the 3 in here, our upper limit, I'm going to get 3 to the 4 over 4. We then subtract 4 lots of 3 cubed. 4 lots of 3 cubed over 3. And then we add 3 lots of 3 squared. And that's all over 2. Okay. And then we subtract the 5 over 12 off. That's our lower limit here for our integral. That's the 1. So if we evaluate this part here, that's the upper limit. And this is the lower limit of the 1 here. So if we evaluate this now on our calculator, in fact, let's simplify first. So I've got 3 to the 4. So 3 to the 4, that would be 81. I get 81 over 4. 3 cubed is 27. So 27 times 4, that's 108. Divide that by 3, and that gives me minus 36. Minus 36. And then 3 squared here is 9 times that by 3 is 27. So I get 27 over 2. Get 27 over 2. And don't forget we need to subtract 5 over 12. So minus 5 over 12 here. We are running out of room slightly. So what I'll do is I'll clear the part at the top just so we can take it to the top then. So we clear this up here. So we've got enough room. Okay, quite a long question. So finish this off now. So this part here, let me do it in a different colour actually, make it a bit easier. So this part here, we're going to take that to the top now. So take that up here. So just put this into your calculator then. So 81 over 4 minus 36 plus 27 over 2 and then minus 5 over 12. Okay. So what I get here then is minus a over 3. So this is R2. Now, like we said, we should expect this to be negative. If we'd got something positive, I'd be slightly worried because obviously this is below the x-axis. So R2 here is minus a over 3. But remember, we take the negation of this, so we take the positive version of this. Okay. So in that case then, R2 is positive. So R2 is positive. So therefore, R2 is equal to a over 3. Okay. So R2 is 8 over 3. So therefore, the total shaded region here is given by R1 plus R2. Okay, so let me just put region here. So in that case, it's going to be 5 over 12 plus 8 over 3. Okay, so 5 over 12 plus 8 over 3. And if you put that into your calculator, what you get here is 37 over 12. Okay, so the shaded region here is equal to 37 over 12. Okay, and there we have it. So that's our solution to that question. Let's just highlight that and hope that solution makes sense there. Okay, so that's our solution to question 3. Moving on to this question here then, where we have a few different things going on. So what we're going to do is just break this down step by step. So if we take a look at the limits first, what we've got here now are algebraic limits rather than numerical. And this does complicate things a little bit, but we'll come back to that in a moment because that's what we're actually going to find here. We're going to find the value of a. So we'll come back to that in a moment. Now for the actual integral here, we need to rewrite this. At the moment, we can't go into integrating this, so we're going to write everything in index notation. So we start with the numerator here, 5 lots of the square root of x cubed. Well, the 5 lots of the square root of x cubed here, well, the square root of x cubed, that would be the same as x to the 3 over 2. So if I times it by 5, I get 5x to the 3 over 2. Okay, so that's going to be my numerator. And then the denominator here should hopefully be a little bit more straightforward. Square root of x is the same as x to the power of a half. So if I rewrite the integral here, I've got the integral from 2a to 7a of 5x to the power of 3 over 2. So 5x to the power of 3 over 2. Let's just write that down. And then we divide it by x to the power of a half. Okay. Now there's two things to mention here that we're missing. We are missing a dx here to tell us that we're integrating with respect to x. So we're missing a dx there. And there's a condition on a here that a is greater than 0. So a is positive. Okay. So find the value of a given that a is positive, or a is greater than 0. So we'll need that for the very end, but don't place too much emphasis on that for now. So we're integrating here with respect to x, and we know this integral here is equal to 450. Okay, we're given that in the question. Now what I can do is I can simplify this here using our laws of indices. So we're integrating from 2a to 7a. So 5x to the power of 3 over 2 divided by x to the power of a half. So in this case, then we can subtract the powers here. So I'm going to get 5x to the power. So that's going to be 3 over 2 minus 1 over 2. And 3 over 2 minus 1 over 2, that would give me 2 over 2, which is the same as 1. So what I get here is 5x to the 1, or just simply 5x. Okay, so I'm integrating now 5x with respect to x. Okay. Now, like I said, this is equal to 450. So this is equal to 450. So what I need to do now is integrate this. Then we're going to substitute our limits in, and then we're going to solve. Okay, so let's actually integrate now. So 5x here, add 1 to the power, divide by the new power. So I'm going to get 5x squared. We get 5x squared over 2. Our limits then are 7a and 2a. So 7a and 2a. And we know all of this is equal to 450. Okay. So what I need to do here now is actually just substitute the limits in here. So we begin with the upper limit here. So I want to get 5 lots of 7a squared. We divide that by 2. So that's my upper limit. Now we subtract the lower limit here. So minus 5 lots of 2a all squared. Like so. And we just divide by 2. And we know this here should be equal to 450. Okay, so we just need to solve this now. 7a squared, that would be 49a squared. Times it by 5, so I'm just going to use my calculator here. 49 times 5. So that's going to give me 245a squared over 2. So I get 245a squared. 245a squared over 2. Minus, so 2a all squared, that'd be 4a squared. Times it by 5, so I'm going to get 20a squared. So 20a squared. And that will be all over 2 as well. And this is equal to 450. Well, we have the same denominator here, a common denominator, so we can just subtract. That's going to give me 225a squared. 225a squared over 2 is equal to 450. We're running out of room a little bit, so let me just clear a bit of room at the top here, just so we have enough room to finish this. Just clear off the beginning lines that we did up here. And we'll just finish this at the top now. So we'll do this in a different color just to highlight that. So we've gone from here all the way to the top. So we had 225a squared over 2 is equal to 450. And we're just looking to solve for a here. That's all we want to do, find the value of a. So I'm going to multiply through by this denominator of 2. I'm going to get 225a squared is equal to 900. We just want a here, so we're just going to divide the coefficient of a squared. So that's going to be divide both sides by 225. So we get a squared is equal to 900 over 225. In this case, this will give me 4. So we get that a squared is equal to 4. So a squared is equal to 4. And that's why we've got the condition here that a must be greater than 0, because we're going to get two solutions here. When I take the square root now, we're going to get plus or minus the square root of 4 here, which would give me plus or minus 2. But if the condition here is that a is greater than 0, then a must be equal to 2 in that case, okay? Which would mean in that case, my limits here would be 2 times 2, so that would be 4 for the lower limit, and for the upper limit then it would be 7 times 2, giving me 14, okay? And there we have it, that's all we're looking to do. We just want to find the value of A. Like you can see, a little bit challenging just to get started, but once you kind of get into the flow of that question, not too bad there. So that's our solution to that question. I'm moving on to the very last question here, so I just go back to my original pen colour. So we're looking at finding an area now, and what I've got here is this diagram, which shows a sketch of the curve. Oops, ignore that y there. So y equals 3x minus x squared, and the straight line y equals x. So what I've got here is my straight line y equals x. And I've got this curve here, this negative quadratic parabola. That's 3x minus x squared. Okay. Now, two parts of this question. Part A, we just want to find the coordinates of the point where the straight line intersects the curve. So where do these two, or the straight line and the curve meet? So I've got this point here, which we need to find the coordinates of, and this point here. Okay. So this one here should be pretty obvious. That's going to be the origin. But this one here we need to find. Okay. And then in part B, we're just looking to find the shaded area using integration. So we're looking for this part here. Okay. So we'll come back to part B in a moment. Let's just see if we can find the coordinates of this point here. Okay. So these are going to intersect when they're equal to each other. So in that case, what I'm going to do then is set these equal to each other. So therefore, for part A, I have x equals 3x minus x squared. Okay. So because I'm dealing with a quadratic here, I'm going to make the x squared term positive. So I'm going to take that to the other side. So I'm going to get x squared plus x is equal to 3x. Now I'm going to subtract 3x off both sides. So we've got it set equal to 0. And then we can solve it. So x squared, x minus 3x, that would give me minus 2x, is equal to 0. Okay. Now from here we can factorize. We can factor an x out. So I get x lots of x minus 2 here. And this all equal to 0. And from here we get our two solutions. We can see one solution here given by x equals 0. So like we said, that would be this point here at the origin. And we also have x equals positive 2. Okay, so this point here, we just go down. This is at 2. Okay. Now obviously we want the y coordinates as well. So in this case, if I just set y equal to x here, then obviously my y coordinate will also be 2. Okay, so y is equal to 2, and obviously in that case, y will be equal to 0 there. Okay, so that gives our coordinates of the point where the straight line intersects the curve. So that's part A done. So that's going to be 2, 2 there, and this would be the origin 0, 0 there. Okay, so that's part A done. Now for part B, we need to carefully consider how we do this, because normally what we do here is we just integrate the curve here, the quadratic, and what that would give us is the area underneath the full quadratic. So if I was integrating between 0 here and 2, that would give me this area here as well under the straight line. Okay, but we don't want that. We only want this shaded region here. So we have to think about how we obtain that area. Now what I've got here is just a right angled triangle. So if I can find the total area here between 0 and 2, and I can subtract off then this right angled triangle here. Okay, I can subtract that right angle triangle off that area, then that would just leave us with this shaded region here. Okay, let's call that R. So for the shaded area, that's going to be total area under my quadratic. That's total area under this quadratic here. So under y equals 3x minus x squared between 0 and 2. And then we're going to subtract the area of this triangle. Okay, so if I call the area of this triangle, I don't know, let's call that R1, let's call that R2. Okay, so R2 is this area here for the right angle triangle. So we're going to subtract R2 then. Okay, so let's have a go then at finding the total area under the curve. So in that case, we need to integrate. So we're going to integrate here this curve. So 3x minus x squared with respect to x. We're going to do that between 0 and 2. So let's integrate here, going term by term. So add 1 to the power divided by the new power. So I'm going to get 3x squared over 2. So 3x squared over 2. And this minus x squared here, again, add 1 to the power divided by the new power. So it's going to give me minus x cubed over 3. Okay. We have our limits here of 0 and 2. And I only need to actually consider the upper limit here. Once you substitute the lower limit in, then this will all be equal to 0. So for the upper limit here, I'm going to get 3 lots of 2 squared over 2 minus, so now we do 2 cubed over 3, so 2 cubed over 3. Okay, so we just need to evaluate this on our calculator. So 2 squared is 4, times that by 3, so we're going to get 12 over 2, so that's 6, minus 8 over 3. So let's do this on my calculator, 6 minus 8 over 3. And that gives me 10 over 3. Okay, so for the total area here, so from here to here, this total area is 10 over 3. So what I want to do now is subtract this right angle triangle off here, the area of this right angle triangle. So what I'm going to do now is I'm going to do the triangle in red. So I'm looking to find this area here now, and then we can subtract that off. So triangle, well, this is a right angle triangle, so it's going to be base times by height divided by 2. So our base here is 2. Our height will also be 2. We're going to do 2 times 2 divided by 2. Okay, so 2 times 2 is 4. Divide that by 2. And 4 over 2 gives me 2. Okay, so in that case then, the area of R1, so to finish with, let's do this in a different colour here. Do that in blue. So area of R1 is going to be equal to 10 over 3, the total area here under the curve, so 10 over 3 minus the area of the triangle, so minus 2 there. So 10 over 3 minus 2, and that leaves me with 4 over 3 there. Okay, and there we have it. So R1 here, that is equal to 4 over 3. Okay, and there we have it. So that's our solution to the very last question. And that brings us to the end of this video on exam revision for integration. In the next video, we're going to take a look at introducing the exponential function.